So how are you today? Good. So let's keep on looking at this, how we solve. So I think I stopped that we were discussing how you in general solve a classical mechanical problems. And maybe the last thing that I have to tell you is you will see that problems fall into general classes. Either you have how to say, you have some configuration of bodies and you are supposed to find the forces, okay? I'll show you an example. Or you are given the force, you have to solve the equation or the equations of motion, okay? These are the two classes. Let's see that in a few examples. We do just Newtonian mechanics because we haven't introduced yet the Lagrangian formalism. So in the first class, probably you have seen many of those. For instance, you have all those problems in which you have planes, tilted planes and masses. You are supposed to find out what are the forces. Just give you, let's see if I have a nice, maybe this one. So let's assume you have a wedge like this, okay? So it's a tilted plane. You have gravity, obviously. And say you have a mass that I call M1 here, sliding on this plane. And then this is connected through a pulley to another mass that is down on the other end here. Okay? Is this clear? So you see, I'm given the problem. I first draw, as we said 2 days ago, I draw a diagram. And of course, you need to know what is the angle here. And as I said, you have gravity that, as usual, points downward in your... this mass here slides on this plane, and there is some friction, okay, some frictional force, and I'll write that as a coefficient mu. Let's call it mu. So this is a typical things you find in any textbook of classical mechanics. Probably you have solved problems like, have you ever, through your training, previous training, you must have solved problems this, okay. It's an idealized situation. And you see, this is a problem in which you are given some mass distribution, some connections, and some external force, and then you are asked, for instance, what are the accelerations here, okay? What is the tension in the string? Let's call it T. So by using Newton's law, you must be able to find out what are the accelerations of these two masses. Clearly, the two accelerations are the same because these are connected by this string. And what is the tension in the string? So let's try. So I'll write for you the. So this tension must be the same here and here, right? And then this guy here, the mass M2 is pulled down by gravity, right? By a force that is M2 times G. Agree? And what is the force on mass M1? Okay, you have gravity that again is pulling down this way. Okay, but of course, because this mass is resting on this plane, you have a reaction from the plane, right? So you have, let's call this N, that is in this direction, and then you have the tension that is pulling that way. Do you all agree? This exercise also serves the purpose of showing you how awkward it is to use Newtonian mechanics. You will see we will solve the similar problem using the Lagrangian, and it will be much easier. You see, I have to worry a lot about all these forces, which way they point out. We will see, but let's solve this. So what I'm supposed to do is to write the Newton's law for each of these components, right? Because these are still vectors, but the Newton's law works in each and every directions, and so I have to write all this. So let's just write what happened in this direction here. That is the direction of the tension. So let me call f, little f. So this moves in this direction. Let's assume that it's moving in this direction because this guy here is pulling down because of gravity. And you know that the frictional force is that force that acts in the opposite direction with respect to the moving object, right? Obvious. So if I indicate this by little f, it's pointing this way here, okay? So along this direction here, I'm going to have T, the tension that is pulling on this mass here, minus whatever this f, little f is, okay? And let's see, I also have what? I have gravity this way, but I have to decompose gravity in two components, right? So one component is going to be this, and the other along this line. So how big is the component of this gravitational force along this line? Well, it depends on the angle, right? And is what? So it's m1 g time sine of theta. Do you all agree? So the sum of all these three forces must be equal by Newton's law to the acceleration of this bob, of this mass. That is equal to m1 times the acceleration. How about in this direction here? Well, in this direction, I only have, well, n, whatever that is the reaction of the plane on the mass, right? Minus, pointing in the opposite direction, the other component that I have of gravitational force on this mass, right? That this time is m1g times what? The cosine. And you see that this is just resting there, so there is no acceleration in this direction. So the sum of these two must give 0. Okay, so this is the second equation. But I have a third equation that has to do with this other mass, right? This is moving in this direction here. In fact, it's pulling down. So if I write that, I have m2g, that is the gravitational force acting on this mass, m2, minus whatever the tension is. And this must be equal to m2 times the acceleration. That is the same because these two are linked together by the string. Okay, so I'm done. I've written the equations, and now I can try and solve. So how many unknowns I have here? Unknowns are things that I don't know yet. I'm supposed to find out what their values is. So how many? So m1 is given, right? G is given, and theta is given. So I don't know A, I don't know 1. T, I don't know. N, I don't know. And F, I don't know. So I have 4 unknowns, and how many equations? So is that good or bad? It's bad. I need one more equation if I want to solve these things. And where does that come from? The friction, right. I have a fourth equation because F that I wrote there by some approximation is usually, not right, is always, I say mu, so it's just proportional to to the n, right? Usually. I mean, this is an approximation, but let's just use it. So 1, 2, 3, 4. Okay, so I'm in business. And in fact, I already know, right, because I can immediately solve the reaction of my plane on my mass. It's already solved, right, because you see everything on this side is known, m1, g, and the theta. So I already know that n is exactly equal to this. So I can already replace this by and this is already done. So the kinetic friction, it's already solved. So what I'm to solve completely the problem, I only need to plug in now this in this term, right? You see? So if I do that, I get T minus mu m1g cosine theta minus m1g sine theta equal m1, the acceleration. And you see that now I have T. I can solve this as T equal, I bring this on the other side. And I plug it in here. And then you see now I'm okay, because m2g minus, in fact, let me write it like this, m2g minus minus this is equal m2a. So now everything on this side is known. I only need to determine what is A, and you see that A is equal to what? I bring this on the other side, and then I have everything on top. So you see I have G everywhere. Then I have M2 minus this term here, that is minus mu M1 cosine theta minus m1 sine theta divided by the sum of these two masses. And so this is the acceleration. And once I know that, I just plug it in here, right, and I can get T. You can do it yourself. And you will see that T is just G m1 m2 1 plus mu cosine theta plus sine theta, the sum of the two masses. So A, T, F, N is already here. And I've solved the problem. Very nice. So I hope this is sort of standard for you. Any questions? Was it standard, or would you been able to solve it by yourself? Or I hope so, right? Or not? Don't be shy. I mean, it's not yes or no. It's a binary question. How many of you would have known how to solve it? Raise your hand. 1, 2, 3, 4. Okay. Never mind. But so let me. So that's a typical problem, and is a typical solution by using F equal to ma, the Newton's law, right? You find all the forces. Let's just see another example, just to. This is still of the same class of problems, in which I give you some configuration of masses, and you are supposed to find the accelerations. Probably you know about these Atwood machines. Have you ever heard about the Atwood machine? mean, it's not very common, but it's very common in textbooks. So you better know it. And it's essentially, so let's use, this is a ceiling. You hang from the ceiling. So it's simply, say, a string again. And then, for instance, you have a pulley here. And let's say you have another one here. And the string goes this way. Okay, and maybe you have a mass here. I don't know if I'm not very good at drawing. These are two pulleys, right? These things you use to pull up stuff. And they are hanging from this ceiling. And from, let's say I call it, you have two masses, M1 and M2, hanging from this, one from the string and one from the center of this pulley. This pulley is free. It can go up and down as you pull this string down. Is this clear, or? Yes? I mean, if I pull this, this goes up or down, depending. If I let it go, it goes down. And of course, you have gravity all the time. This kind of many pulleys and strings and masses attached is called an Atwood machines. And you'll find many exercises. It's just nice because you can apply Newton's law and find out, for instance, the tension. What is the tension in the string? And what is the acceleration, again, of these two masses? So again, let's just apply Newton's law to this simple system. Okay? So what is, if the tension here is T, the tension here is going to be twice as much, because. So if I look at the at this part, right? If I look at the mass m2, so if I want to find out what is the acceleration of the little mass m2 that is hanging from this pulley, right? So the acceleration of this is going to be what? Well, it has gravity pulling down, right? But you have twice t pulling up. So it's the difference between 2t and minus m2g. So this is the Newton's law for this point here. Similarly, Newton's law for the other mass there is m1, a1 now. They are not, it's not like before that they had the same acceleration necessarily. Here they can have different accelerations. So I have a sub 1 and a sub 2. Yes, is t minus m1g. So again, I have to ask myself, how many unknown quantities do I have? And you see that you have 1, 2, and 3. And again, you are short of one equation, so you have to figure out where that equation comes from. Any idea? You see, there is a sort of, if you call, right, if you call the position, so let's call this the y-axis. And if you call the position of this mass y1, right, you see that the position of the other one is sort of linked, because if I move back and forth, so let's I don't know, if this moves up here, right, by an amount y1, this one at the same time moves down by an amount that is twice that one, you see, because this goes up, say, by y1. But you see, you have twice as much string here that it goes down there. So this one moves down by twice that amount. So there is a sort of conservation of the string lengths that tells you that the position of, I'm sorry, yeah, I'm sorry. This let's call this y1 and this y2. So you have y1 is equal minus y2, right? twice as much, as I said. So because if I move by y2 that month, I get twice as much string that flows down this way, and so this one goes down by twice as much, and that's why you have a minus. This goes up, this goes down. So you see, this is a sort of a conservation of the length of this string, and it gives you this relation. Now, if I take twice the time derivative of these positions, I do get that A1 must be minus 2A2. And this is my third equation, that necessarily the two accelerations are not equal, but they are related. In fact, one is twice as big as the other one, and of course pointing in the opposite direction, because as one goes down, the other goes up, because of the string. You agree? Why is twice? Because you see, the tension is the same, but here you have pulling this way and this way, so it's like twice as much. So in this direction you have 2t, and down the other one. It's pulling up. It's like you're pulling with two strings, so you have twice as much. Okay? Now that we have three equations for three unknowns, well, it's trivial to solve. Well, is your pick. You can solve whatever. I'll just give you the solution. It's just an algebraical problem. And T is 3 times the product of the masses times G Okay, not very exciting, I agree, but it's a fine example of how you can use Newton's law, again, to find your solution. So these two problems were examples of the first kind of problems that you will be asked to solve in general. You see, you are given your masses in some external force, gravity here, and then the question is how they move, so find the accelerations, the tension, all the forces. The mass.
Okay. So, M2, une condition d'équilibre, M2 multiply G, you call
No, this is free.
yes. Okay.
Is hanging around this string. Okay. And this is weightless, everything. So the mass is idealized by this M2. Okay, you draw. Yes.
Constant équilibre, this force equal this, okay?
Yes.
This is resultant.
Yeah, is that the equation here?
Yes. Yes, mais this force, okay? Yes, okay.
No, they are like this, right?
This,
This is pulling, so this pulls T, and also you have the reaction from here, so you have 2T. Minus the weight.
the way this is in equilibre, this is
Yes.
so this force resultant.
No, they are not. If they are not equal, you have an acceleration, and I call this A2.
Thank you.
So, I mean, for each of these two components, is like if I had a point particle here, M2A2, and the net acceleration, the net force is 2T minus this. And that it moves. And the same is here. Now, what is the other kind of general type of problem. Yeah.
How is if those things rotate on the string?
No, it's just it's sliding. I mean, I don't know how. You take a disk and you assume that it's weightless. And then you slide a string, okay? So this can move up and down. This, and everything is weightless. Then the only weight in this problem is this little mass hanging from there. I mean, it's idealized. I mean, it's not realistic, but.
We can consider that the rotational degree of freedom.
This, yeah, but because this is weightless, it doesn't matter. You are thinking of moment of inertia, all this stuff, but we want to keep this stuff simple for the moment. It's weightless. Everything is weightless except these two little masses, so there is no rotation, really. Okay? Any other? So let's just look briefly to the other kind of problem that I said is the other possibility. Now, the other... The other kind is when you are, so I said, you are given some initial conditions and some forces, and you are asked to find out the trajectory. Now, the most typical one is one we already mentioned, is that, say, for a given speed, say, you throw something. You remember 2 days ago, the problem of throwing that ball from a cliff. So let's just discuss something similar. So you throw something with a given speed with some inclination angle, okay, with some initial velocity. So you throw, say, a ball with the initial velocity v, and you throw it at an angle theta with respect to the horizontal plane. So you are asked to find what is the, as I said, what is the best, the angle for which it travels the farthest. Okay, that's a very famous problem. We already, it was very important, you know, when they had guns during the ancient time, they wanted to fire a gun, you know, to the enemy that was very far away. And so what is the angle for which, given the initial velocity, you hit your enemy the furthest? Okay, that's a very interesting question, because probably you already know the answer, but let's derive that. Maybe somebody wants to solve it for me, or what is the answer? Do you already know that, or what? Yeah, what is the best, well, I mean, what is the angle? Right. Why do you say ideally? What I'm neglecting here? The air, right? And what if I include the frictional force from the air? What is the angle? Is it higher or lower? Higher. Why? That's a very important question. You know, in World War I, you know, in Europe we had many wars, so we numbered them. So in World War I, the Germans had a very big gun, and they wanted to fire on Paris, that is a city, the capital of France. But it was very, very far away, and so they knew that, as you said, this approximation was not good, because the shell had to travel through air. So they had to compute it there when they first computed that. So you said it should be higher, right? Why? How does the density of air varies with the height? If you go up in the mountains, is the air thicker, less, right? It becomes. So you see that if you allow your ball or your gunshot to travel higher, it will travel where air is thinner. So less frictional forces. So you gain by going a little bit higher than down, you gain some distance, because you travel through some part of your path is where the air is thinner, less frictional forces. So they knew that they shouldn't fire by pi over 4, the 45 degrees. They should fire a little bit higher, and then the gunshot will go further and hit Paris. But OK, let's write the solution for just. There are many ways to find this solution, but so first you decompose this velocity, right? You have this velocity has two components. Say I wrote x and y, so I put some coordinates, and Vx is obviously V cosine theta, and Vy is V sine theta. Okay. Then the other nice things about Newton's law is that the two components act independently in a way, right? You know that the only force is G and is pointing down along the y directions. So the x directions behave as if there were no gravitational force, right? You know that. That's the nice things about decomposing the... So what are Newton's laws? So in the x direction, that is this direction here, perpendicular to gravity, what is the acceleration of your ball? 0, because there are no forces, so there is very simple. And in the other direction is just g, and for the since I decided to have y pointing upward, is going to be minus g. So I only have to solve these equations, and I'll find my solution. Okay, so this is the other kind of problem, as I said. You see, it's slightly different. I don't have a configuration. I have to look for the acceleration by putting terms one equal to the other. I have the differential equations, and I have to solve them. Second order differential equations, of course. So I need the initial conditions, but the initial conditions are exactly this, right? Because let's take, so x dot, what is the initial velocity is just, so at time, well, at time t equal to 0. Well, actually, I can, so I have to solve this. So this I can do it right away, right? Because I just have that x of t is to be some initial condition plus my Vx times t, and that's it. Right? How about this? This is so x. So the dot, say, is going to be the initial value that I call Vy minus gt, right? Therefore, by just integrating this, I have the position that is just Vy t minus 1/2 gt squared plus whatever is my initial position, okay? Is this clear? I mean, no? Then stop me. Otherwise, you are going to be dead if you don't stop me, because we move to the next subject, and you. So what is not clear here? This is the solution of this differential equation. How do you solve this differential equation? That's is the dots, you know what it is, right? This is the second derivative. This equation is the second derivative of x of t with respect to t equal to 0. So I integrate once, and I get the velocity, right? I get that the first derivative of x of t with respect to t must be equal to what? To a constant, right? Because I know that if I take the derivative, I get 0. So let's call this constant v of x. And I know what v of x is there, right? Now I have to integrate this one more time. And what is the integral of this? This will be x of t is the integral of this with respect to time. And of course, plus any constant that is arbitrary, and that this constant is the initial position in the x direction, so the position at which I'm throwing this ball, and this other constant is the initial velocity with which I'm throwing the ball. How about the other one? Is just similar, but you have to worry about this. So at the first step, you already have a constant, so you get Vy, right, minus gt for the velocity. And when you integrate the gt, you get 1/2 gt squared. Is that clear now? Any other? I assume that this is okay. So I have here my solution, right? So what is the distance that this thing travels? Well, you can just find it from there. I like to do it this way. If I find the time it takes to fly there, then I'll find also the distance. And how long does it take? Well, notice this. If I take the velocity in the y direction, right, I know that if I compute this half time, so at halfway, right, what is that? How? 0. A very nice number. Is this clear? Because if you throw something, it goes up half the way, right? It's a parabola, you know, and then the other half goes down. When it's exactly halfway, it's not moving up any longer, and so this must be true. So that's a nice way to find the time. You see, because you know that this is what? The velocity is written there, right? So this thing here is just that the Vy is equal gt half, right? Y dot t is just Vy minus gt, right? So if I put t and a half, and this must be equal to 0, I get this. And how, if I call d the total distance traveled by my ball after I throw it, how big is that? D is in the x direction, so it's in this direction, right? So it's just, so x naught is here. D is whatever is left, so it's just Vx times t, right? But t, I have it here, is just twice Vy divided by g. So I found twice Vx Vy divided by g. And what is Vx and Vy in terms of the initial total velocity and the angle? You see, I can just plug in these two to get 2v squared, 2v squared sine theta cosine theta divided by g. 2 times sine theta cosine theta is also known as, right. So now I have the distance, right, as a function of my known quantities, and in particular of these two theta. So for what value of theta I get that d is the largest? Well, I have v squared over g is fixed. So I can only vary sine 2 theta, and you know that the sine goes from minus 1 to 1. You want that to be the largest, right? So, and so for what value you get there 1, you get for theta equal as your colleague pointed out earlier. Okay? So these two were typical, these three were typical problems. And now I'm essentially, yeah. So you saw that they were, what makes these problems a little bit difficult, especially the others. This one is sort of, you see that let me, one final problem, and this time I stop and point out the difficulties. I mean, difficulties, so to speak. I mean, but still. So let's go back to the problem with the wedge and the little mass on top of the wedge. But let me change it a little bit, because otherwise, I mean, it becomes really too boring. So this time, I put this wedge on a plane, a frictionless plane, so that I have a big M is the mass of the full wedge, a little m is the mass of the little mass on top of this wedge. Okay. So there is this block of mass m, and is held there, motionless, on this frictionless plane, on this other block of mass m, big M, and the inclination angle is theta. Okay. So everything is frictionless this time, to make it easy, and you are holding this mass there, because if you release it, it will slide down. So, and the question is, so the question is, now I release this block here, the little one, and you know that this will slide down, and this is going to move in this direction because of conservation. And the question is, what is the horizontal acceleration of this block? Okay, so it's a twist of the previous problem. So first I'm going to solve it using Newtonian mechanics, so that I will point out what is awkward about Newtonian mechanics. I mean, it's perfectly fine. If you like Newtonian mechanics, there is no problem in the world that you are not able to solve. Well, there is no problem in the textbooks that you won't be able to solve, but so you can keep on that. But we are here to learn a different technique. So let's see what we can do better than just use it. So first, let's again write this. You see, it's similar to the problem I discussed before. So I need to write component of all the forces. I have, as before, I have a reaction from the I call it n, from the fact that this mass, this block here, is resting on top of the bigger one. And of course, here down, I have my mg, the gravitational force. So again, I decompose along some axis. So let me call, as before, I call x this direction here and y this direction here. So what I'm supposed to do, you see that I have that. Now let's look at this y direction, right? So the acceleration of the little mass in the direction y is equal to what? Well, I have the component of n along this direction, right? And then I have mg. So I can write this mg as before. N projected along this, so the cosine of theta. Then I have the acceleration of the little block in the other direction, the x direction. So I have mi sub x. And what is that? Well, in this direction, there is no gravity. I only have the other component of the reaction. That is n sine theta. But you see, since I also want to find out, in fact, the question is, what is m big AX? So let's call this is the big AX, that is the acceleration of the big block. And you see, this must also be, in this direction, I only have this. So this must also be equal to that component of the of the reaction. And again, I have to ask myself how many unknowns I have. 1, 2, 3, 4. So it seems that is a rule that I'm always short of one equation. And this is always like this because the remaining equations comes from the geometrical distribution of your problem. And you see here that the fourth is given by the fact that this block must remain on this plane. So in other words, I must be able to if I write the position the position of the block as a function of, so let's call it x and y. Right? What is the position of this? It's just whatever this acceleration is, right? Times. Let's start counting from 0, okay? It starts from rest, so initial velocity is 0. The y component of the motion of this little block is simply whatever the acceleration is. I don't know yet. I have to solve it, but let's write it here, times the square divided by 2, right? And the x, by the same token, is what? Is the acceleration in the x direction, but notice now that also the big blocks is moving in that direction, so it's going to be the sum of this plus the big A times t squared. Right? Or not? I can say if I had solved the problem, I would have known AX, big AX, right? Let's assume that I know them. Then I know the position, let's call X and Y the position of this little block in the XY plane, right? Now, this little block in the Y direction, it will be where? I start from the initial position Y, I define it to be 0. It starts out with 0 initial velocity, so it will just move by 1/2 t squared, whatever the acceleration is, by the usual, right? You integrate Newton's law twice, and you get this 1/2 t squared. The same is true in the x direction. The only difference is that in this direction, also the whole system can move, so I have to add to the acceleration, to the intrinsic acceleration of the little mass, also the acceleration of the big one. So I get the sum of these two, and that gives me the position in x. Yes or no? Now, this is true, but I also have, now I can implement the constraint that this mass, whatever it is doing, it must stay on this plane. And how do I do that? Well, to stay there means that y over x must be equal to the tangent of theta, right? Because of trigonometry. And then you see that you get, now I plug in y over x, you see the t square simplify, and I get simply that ay divided by ax plus big AX. And this is my fourth equation. So in other words, my fourth equation comes simply by the requirement that as this little block moves, it stays on top of the big one by this constraint here, that the ratio between these two quantities must stay equal to the tangent of that angle. Okay, so now I have 4 equations. This I can forget. And I have 4 unknowns, so it's just an algebraical problem to find the solution. For instance, you can solve this, right? because AY is just G. I take the mass and divide everything by little m. There is some other lectures that is interfering. And the same for here, AX equal n divided by m sine theta. So now I can take this and replace them here. The same for big A sub x. And you see that I get that tangent of theta must be G minus n over m cosine of theta divided by this 2, that is n over m, plus n divide big M sine theta. And therefore, you see, everything here is known except n, so I can solve for n, and I get that n is equal, if I did it right, and now I'm in the position to answer the question that was posed by the problem. What is big A sub x? Because now I have big A x is just n sine theta divided by m. N is given there. So I just have g sine theta, right, divided by you multiply by m, and you get, so you see you can bring m upstairs. That is nicer. So you have m g sine theta cosine theta m plus m sine square theta. If you massage the trigonometry there sufficiently. Yes? Hmm? What?
Because, for instance, if the small
No, I miss. No, x.
half equal to x is equal to the first x.
This?
Yeah.
1/2?
X minus.
No, because I'm counting this way. I put it. Okay, you can put my minus, but it depends how you write this.
X, we consider small x to be this way and to the right, capital
Yes.
to the left, so there has to be minus sign there.
Because you see, I call ax to be the component in the minus x direction. So, but you can do it. I mean, you can change the sign. It will. Then it will give you the opposite direction. You see, I call ax the component going minus x. So it's up to you. I mean, but it's okay also if you put the minus. Mm-hmm. No, you don't. You look unhappy. No, but actually, let me see. Because actually, you want to sum them, right? Because you have this thing here. This slides this way, and this slides down this way. If this slides faster, this moves, accelerate faster, right? Or not? I'm wrong.
For instance, if we take a small x to be 0, like the mass is resting on top.
This equal to 0.
A small
Ah,
x, yeah.
yes.
Then x has to be minus
Yes.
So that's a switching.
Okay, yes. Okay, then. Okay, but so then if you put minus, then you end up with a minus here. So, I mean, it's the same thing. So I don't see the difference.
Actual my
I mean, it will be minus because you are counting with the x in this direction.
maybe the answer is the same. Yeah, sure.
So, because if you put a minus here, you end up with a minus minus here, and I guess minus here, right? So, and I call this minus x, I call it x. So at the end, it's the same. I think it's the same. So, any other question? Or you see, there are two things that are a bit complicated here. One of these is that you have to deal with vectors, right? Because you see, you have to be careful in projecting all the components. I mean, vectors are nice, but very often they give rise to more, you see, you have to keep track of all the components, you have to be careful. In a way, you have to think, right, to solve the problem. And it's always nicer not to think. I mean, if you know a rule that you just crank in, then this is more efficient. And the first step would be not to have vectors. I mean, if I didn't have all these vectors, but only scalar quantities, you know about scalar quantities, right? There are quantities that are just numbers and quantities that are vectors, right? And Newton's law is based on vectors, so you have components. And vectors are nice as long as you write the equation in vectorial form. But anytime you want to compute something, you have to project out the components on some axis, and then things become complicated. This is not true for scalar quantities that are just numbers no matter what you do. I mean, it's just a number like the temperature or something. You don't have to project out components. You can work directly with scalars. So if instead of having vectorial quantities, we had scalar quantities, maybe we would be better off in solving the problem. The other big things here, the other things is that, you see, I keep on worrying about constraints here. The problem is really that I have the constraints like this one that I have to implement into the problem before I solve it. This is why I was always short of some equations, because the problems was given, but they were not allowed, I mean, the pieces of your problem, like this one and this, were not allowed to move freely. They were constrained. They were only allowed to move in some directions, and this has to be implemented in my problem. And as before, it was always implemented and giving you the missing equation. But this, again, you see, is not something that you can do every time the same way. Each time you have to stop, think, and realize what the constraint is, and then implement it. And this is not efficient, again. So let's see if there is a better way. And first I do it without any explanation. I give you a recipe and see that we get the same answer, but in a simpler way. And then we will spend maybe next lecture to show that the trick I show you here is actually equivalent to Newton's law. Okay? So let me first solve, again, this problem, but in a weird way. Well, I mean, weird if you never heard about, do I need the, well. So I have the same problem. So but let me draw it a little bit. You see, I know that you don't like this, but again, the reason why I have this acceleration in that way, that I count this way. This way I count this positive. Back here I count positive in the other direction. And I do it again, so you are going to be unhappy again. This time I call x1 when I count from the axis in this way, and I call x2 in this other direction. So I put my wedge here, so the movement of my is the same problem as before. I'm just drawing my axis differently. So this is x1, and this guy here is on top, and this is x2, the amount that moves there, okay? So x1 plus x2 is the relative distance from here to here, right? And I switch the sign as before. Actually, this is useful because, as you will see, the way you pick your coordinates is the way you get rid of the constraints. And we will call this coordinate generalized coordinates, but let's wait for that for a second. You see that so this is the little mass m, same problem as before, and this is the big mass m, and this is theta again. So the distance in the y direction is x1 plus x2. So this is, if you wish, is y. The height fallen by the block as it moves is this sum here times the tangent of that angle. So these are the two. And now I say, now consider the following seemingly silly combination of, you take the kinetic energy minus the potential energy of this system. Okay, just take it. So what is the kinetic energy of this system? The kinetic energy of the system is the kinetic energy of this block plus the kinetic energy of the little block. Now the kinetic energy of the big block, it has only one component because we said that this is resting on this floor. It can only move in this x direction. So this is what is the kinetic energy of a block of mass m that moves with velocity x1 dot. Right. So I have 1/2 big M x1 dot square. This is just for this block, okay? But I also have the kinetic energy of this guy, and this is made of two pieces because this can move both in the x direction and the y direction. So it's going to be 1/2 the little mass m. Now it can move in this x, so it's x dot square, but it can also move in the y direction, so it must be the dot of this quantity square. Yes? You want to ask something? No. Yes. Huh? The y is the, so this is x and this is y. Sorry, this is y and this is x. So y is by, this moves down, so by how much it moves down as it moves is x1 plus x2, the component projected in this direction. So is this tangent theta. So this moves down, right? So it moves a little bit in the x direction and a little bit in the y direction. And the y direction is given by that. So if I take the velocity is x1 dot plus x2 dot, tangent theta is the constant, so I just take the square of that, and that is the other component. So x1 dot plus x2 dot square, tangent theta square. What is the potential energy of, well, the potential energy of this is 0 because you can always redefine, it's constant. And I can always redefine a constant to be 0. So the only potential energy is this, as we have G, right? So it's going to be minus mg y, right? Because y is the height from which I'm measuring this potential energy. So I said take this combination that I call L, that is the sum of the kinetic energy minus the potential energy. So minus minus is plus. Sorry. So now, you see, I'm dealing with the kinetic energy and the potential energies, and these are scalar quantities, right? They are not vectors. The energy is a scalar quantity. And now what do I do? Now I give you a way to derive equations from this quantity. And so I just say, now take this equation. You take the total derivative of the partial derivative of this quantity, and you put it equal to the partial derivative of this quantity with respect to x, where x is, you see, you have can be 1 or 2. You know the difference between this derivative and this derivative? What is the difference?
When we say partial, we keep the rest in fixed and then we change.
Right.
Yeah. When it's full derivative,
You hit the dependence even if it's... So is that clear for everybody? If I take the partial derivative, so say you have x of t, right? For instance, you have a trajectory. If you take the partial derivative with respect to time of x of t, what is that? Is? No, take the partial derivative. Right. So, no, but say I take d dt of x of t, where so there is no explicit dependence of t here, right? So this is going to be 0, right? But if when I take the dot, I take the total derivative. No? I mean, the total derivatives means that you go and look into the function until you find that variables, and you take the derivative. The partial derivative is there only if that function explicitly depends on that variable. No? Say, for instance, the velocity is the total derivative of your position in time, right? Because it is, but the partial derivative it can very well be 0 if you don't have an explicit dependence on time here. For instance, so say x of t is x naught cosine of omega t, very famous. X dot, the total derivative, is different from 0 clearly, and is, minus theta sine of that. But the partial derivative of this is just 0, right? Because there is no explicit dependence.
Actually, I don't know, but if the variable is same, then the partial is equivalent to the...
Yes, but in general, not. If you are... I mean, otherwise, why you... I mean, you need two different notation because they are two different things.
Yeah, there are symbols just we implement for that. We use the partial for higher dimensional space, and then we use that. Actually, we use both. Okay.
Yeah, you need more than... I mean, if you only have one. So here I take the total, no, okay.
Here, how are you finding out whether there is explicit say that it is zero because there is no explicit term.
Yeah, no, this is not actually a very good example. I realize after, I mean, you should have something that depends on t, but not explicitly.
What do you mean explicitly?
That you have t explicitly there. Let's have another example. You see, for instance, look at this expression, right? This depends on x1, x2, theta. Now, if I take a partial derivative with respect to t of this, I mean, it's true that this depends on t because it's a trajectory. Why not? It depends on t. But it does not depend explicitly. So if I take the partial derivative of this quantity, it's 0. But if I take the total derivative, that's not 0. I have to take accelerations here and there. So that's what is that. So this is not a good example actually, because there you have. But this is a good example. If I were to take the partial derivative with respect to time of this, it would be always 0, but not because this does not depend on time. It depends on time, of course. It's the velocity as a function of time, but not explicitly. So that's why I need two different symbols. Is that okay now? So I write this equation. Let's write it for, I think, for x1, because that's what I want to find. So my claim is that I wrote this quantity, a scalar quantity, an arbitrary combination of kinetic energy minus the potential energy. I crank in this equation, and I get exactly what I had before by going through all this reasoning of comparing different terms from Newton equation. Let's see. What is now the partial derivative of L with respect to x1? So I have to look for, right, where you have x1, and I take the partial derivative. Okay, so this is mg tangent theta, right? x1. Now, what is the partial derivative of this quantity with respect to x1 dot? So I have to look where I have x1 dot and take the partial derivative. So this term here is, I have this m x1 dot, right, because the 2 cancels out, plus I also have this one. So I have 2m x1 dot plus x2 dot, the tangent square theta. And nothing here because there is no velocity. But I have to take the total derivative now of whatever I have here. And so you see now I take the total derivative, so I add a dot. And I add a dot. And I add a dot. And nothing here because this is a constant. So this equal to this is my first equation. And of course I have two variables because I have x1 and x2. So I also need the other equation, that is the one that I get when I put x2 here. And I do the same. And you see, if I do the same, I get something similar. Because now I have from here the, right? You take the partial derivative, again, you do this. Here you get mx2 dot plus now the same here, m x1 plus x2 dot dot tangent square, right? But I have to take the total derivative. So again, I have dot, dot, dot. And this must be equal to the partial derivative of this quantity with respect to x2. That is just equal to what I had before, because they enter in a symmetric manner. So you have this equation and this equation. And now if you solve, for instance, for, well, you want to find what is the acceleration. So you want to find x1 double dot. And you see that if you take x2 from here, let's do, you can check at home. Take x2 from here, right? You can solve it. And then you plug in there, and you get x1. And you get exactly what we wrote before. That is, the acceleration of this block going in that direction is given by this quantity. So up to now, this is just as, it looks like magic, it looks like a trick. I arbitrarily introduced this quantity, L, that I define to be the sum of the kinetic energy minus the potential energy. Then I ask you to believe me that if you use these equations, you get exactly the same equations that you would have by using Newton's law. And then you solve. Indeed, you get the same result. But you see, there were two nice features that we had here that we didn't have before. The first is that, as I said, I'm dealing just with scalar quantities. This time I didn't have to worry that this component was summing to the other one, the other was summing to the other one, and they were balancing off nicely. I just crank in. I can even forget, once I write this Lagrangian, then I keep on going just by using the equations, and I don't have to really think about it. And the other thing, you see, because I pick these coordinates in this way, I sort of, you see, I never mention about constraints. Of course, I picked the coordinates in such a way that this problem was not there, but this is exactly the other part of the trick. You define your coordinates not as x and y or some given, but you pick your coordinates in such a way that they are independent from each other, and in this way the constraint is taken into account automatically. Okay, so these were the two ingredients. And of course, this function, I call it L because it's what is going to be our Lagrangian. Yes?
Yeah, x2 is not dependent on x1. Why?
X2 is not dependent on?
x1.
No, they are two independent.
Yeah. Now, the partial derivative in respect to x1.
No, this is now it's x2.
Yeah.
Whoa.
It's the same. Yeah.
Where you come. So you have two equations here, one for each. The first time you take the derivative with respect to x1 dot and x1. The second time x2 dot x2. There I take the total time derivatives of whatever I have here. So then I add the dot. A dot for me is the total derivative with respect to time. You agree, or? Well, don't leave. I mean, tell me if you. Huh? Is that okay or not? I mean, first you take this derivative and you get this expression, right? Now you have to hit this expression with the total derivative with respect to time. So what happened? When you get here, you add the dot. When you get here, a dot, a dot.
If you completed the partial derivative of
This is the partial derivative of L, of this function, with respect to x2 dot.
dot, yeah.
So I take this term here, at this term here.
Why x1 have
This? Yeah, but what is the partial derivative of this? It's twice x1 dot x2 dot tangent square. What is the derivative? What is this? That's exactly what you have there. When you take the partial derivative, you keep everything else fixed, and you take the derivative. So it's like here. This is a constant. The derivative of x with respect is just twice x plus a. You don't agree? No, I mean, huh? What do you mean expand? No, but you don't have to expand. Okay, you can expand, say x squared plus 2. So what is the derivative of this? 2x plus 2a, that is also known as this. Is this better? Okay. Any other questions? Okay, so we stop here. I've introduced, without any explanation, this function and this equation. So next time we try to convince ourselves that in fact these equations are equivalent to Newton's law. Okay? And I hope that I convince you that there is an advantage in switching to this other formalism, because as you will see, then you can solve all problems in a more efficient and automatic manner. Okay? Any other